Hello, everybody. We are continuing today with lecture 14, part 1. This numbering the lectures is only a way to, to keep tabs, nothing else. And also I try to be in accordance with the lecture notes I'm sharing on ODTÜ class, Özgür Kişisel lecture notes from last semester. Okay, so in this lecture, I will try to give you more examples about homogeneous linear ordinary differential equations with constant coefficients in the case of distinct roots of the characteristic equation. So let's quickly remember what's all this. So we are talking about homogeneous linear ordinary differential equation, nth order, with constant coefficients. So we have n real numbers, constants. And we consider the differential equation, the nth power of our function y plus a1 times n minus first derivative of y plus, we keep going this way, an times the function y equal to 0, because at the moment we are only considering homogeneous equations. Now we have the characteristic equation, Pn of lambda, the polynomial. We just take the coefficients of our equation. So we start with lambda to the n plus a1 times lambda to the n minus 1 plus an minus 1 times lambda plus an equal to 0. This is our characteristic equation. And we considered the case where this equation has n distinct roots. In this case, the functions e to the lambda 1t, e to the lambda 2t, up to e to the lambda nt give independent solutions. Okay, so let me consider more examples. In the first example, we have an initial value problem. Solve the initial value problem given as second derivative of y plus 3 times the first derivative of y plus 2y equal to 0. And the initial conditions are the value of our function y at t equals 0 is equal to 0, and the derivative of our function y at t equals 0 equal to 1. Now, initial conditions for second order differential equation, since for a second order equation, in the general solution, we are going to have two independent solutions. We are going to consider their linear combination. So in the general solution, we are going to have two constants. Now, in order to obtain a unique solution, we need two initial conditions. And initial conditions have to be at the same point t0. So in this problem, the point t0 is 0. So only giving the value of our function y at 0 is not enough. We also need the derivative, since for second order equations, we need two initial conditions. Okay, so first we are going to obtain the general solution, and then using the initial conditions, we are going to find the constants. So to find the general solution, first we need to consider the characteristic equation. The characteristic equation is lambda squared plus 3 lambda plus 2 equal to 0. And the left side can be factored out as lambda plus 1, lambda plus 2 equal to 0. So the two solutions, two roots, are minus 1 and minus 2. We have distinct roots. So both of them are real. General solution then, constant C1. For lambda 1, we have the function e to the minus 1 times t plus C2 times, for lambda 2, we have the function e to the power minus 2 times t. Now, this is the general solution for any constant C1 and C2. Now we use initial conditions to find C1 and C2. Okay, let me rewrite the initial conditions here. Y0 equals 0 and y prime 0 equals 1. All right, so since the value of our function y at t equals 0 is 0, in the general solution, we substitute 0 for y and 0 for t. If you substitute 0 for t, e to the 0 is 1, plus c2 times e to the 0 is again 1. So we have c1 plus c2 equal to 0. So we can say, for example, then the constant c2 must be equal to the constant minus c1. To use the second initial condition, y prime 0 equals 1, first we need the derivative function. We need y prime t. Now y of t is c1 times e to the minus t plus c2 times e to the minus 2t. So the derivative of e to the minus t is minus e to the minus t. So minus c1 e to the minus t. And derivative of c1 is a constant. So derivative is 0. c2 is constant. Derivative of e to the minus t is minus 2. Don't forget the constant c2 times e to the minus 2t. And now for the condition y prime 0 equals 1, we use 1 for the value of the derivative and 0 for t. So minus C1 minus 2C2. But from the first equation, remember we have the condition C2 equals minus C1. So 1 equals minus C1 minus 2 times minus C1. So this gives us plus 2 minus 1. This gives us C1. So C1, the value of the constant C1 is 1. And since C2 is minus C1, the value of the constant C2 is minus 1. So that means the solution, the unique solution of the given initial value problem, we use 1 for C1 and minus 1 for C2. So e to the minus t minus e to the minus 2t is the unique solution of the initial value problem. Okay, so let's summarize what we do to solve such a problem. First, we write the characteristic equation using the coefficients in our differential equation. We find the roots of the characteristic equation. So first we write the characteristic equation, then we find the roots, and using the roots, we write the general solution. And then we use, in this general solution, we use the first initial condition to find the first equation. And using that first equation, we find a relationship between constant C2 and C1. And then, in order to use the second condition, we need the derivative. So we take the derivative of our function and use the second initial condition. And in that initial condition, we use the relationship we find from the first equation to find one of the constants, and then that gives us the other constant. So using those values of the constants, we write the unique solution of the initial value problem. Okay, let's see. Did I do? Okay, yeah, fine. All right. Now, another example. Find all solutions. So this is not an initial value problem. We are just going to write the general solution. Find all solutions of 4 times the third derivative of y plus y prime plus 5y equal to 0. Now, this equation is not given in the standard form. We have a coefficient in front of the highest derivative, but that doesn't change anything because it's an homogeneous equation. So on the other side, we have 0. That means we can divide by 4 and it will still be equal to 0. And once we write our characteristic equation, it's again in the characteristic equation, we have a polynomial equal to 0. And in that equation, now we can multiply by 4. Again, it doesn't change anything. So even if we have a constant in front of the highest derivative, which is not 1, we can still continue in the same way. So first we write the characteristic equation. Using the constants in the differential equation. So 4 times, since it's a third derivative of y, 4 times lambda cube plus y prime, so that's lambda plus 5 equal to 0. So this is our characteristic equation. Now the characteristic equation is of degree 3. So we expect 3 roots. To find all the roots, it's not clear how to factor out this polynomial. So in this case, we try to guess one root. So how do we do that? Try some numbers, like 1 minus 1, 2 minus 2, and if it doesn't work, 3 minus 3, and so on. Since all the signs are positive, I think it's clear that no positive number is going to be a root. So let's try a negative number. So try minus 1. So minus 1 cube is minus 1 plus minus 1 plus 5. It is equal to 0. Lambda equals minus 1 is, so let's say lambda 1. Equals minus 1 is a root. All right, so we obtain one root. How do we get the others? Once we get one root, this means there is the factor lambda plus 1 is a factor of 4 lambda cube plus lambda plus 5. So we try to write our polynomial as lambda plus 1 times a second degree polynomial. So that the second degree polynomial times lambda plus 1 should give us 4 lambda cube plus lambda plus 5. You can try polynomial division, or you can try to find the terms of the second degree polynomial one by one. So first we have lambda. To get 4 lambda cube, we need to multiply lambda with 4 lambda squared. But then this gives us 4 lambda squared. There is no term with lambda squared on the left side. So to cancel out the 4 lambda squared, we need minus 4 lambda squared. That means multiplying lambda with minus 4 lambda. But then this gives, when you multiply 1 by minus 4 lambda, we get the term minus 4 lambda. But on the left side, we have just lambda. So to minus 4 lambda, we need to add 5 lambda. So we multiply lambda with 5. So this gives us lambda. And then multiplying 1 with 5 gives us the constant 5. So we factored out our polynomial as lambda plus 1 times 4 lambda squared minus 4 lambda plus 5. As I said, you can find the second order polynomial, 4 lambda squared minus 4 lambda plus 5, by using the polynomial division. All right, so if we set this equal to 0, we already have the first solution, lambda 1 equals minus 1. And then we have the second order polynomial equal to 0. It's not clear how to factor it out, so we use quadratic formula. we have lambda equal to minus 4. So 4 plus or minus square root minus 4 squared is 16 minus 4 times 4 times 5 divided by 2 times 4 divided by 8. So under the square root, we have the common factor 16, and 16 goes out of the root as 4. Then for 16, we have 1 minus, for the other 16, again, we have 1 times 5 divided by 8. So we can simplify the 2 4s by 8. We have 1 plus or minus square root of minus 4 divided by 2. So we have 1/2 plus or minus. Since we have a negative number under the root, we have the imaginary number I. Then square root of 4 is 2 divided by 2 gives you 1. So the other two solutions are complex. We have the second root, 1/2 plus I, and the third root, 1/2 minus I, which is the conjugate of lambda 2. Remember what we do if there is a complex root. Lambda equals A plus I times B, where A and B are real numbers. Then the corresponding solutions are, we use the real part, the number A, to write our exponential function, e to the at, and we use the imaginary part, number B, to write the trigonometric functions, cosine bt, and we also have sine bt. Remember, although the roots are complex, we need real valued solutions. So we take the real part and the imaginary part of the solution. That gives us 2. For a complex number, lambda, complex root, we get 2 solutions. So we don't need to consider the complex conjugate, because the complex conjugate is going to have the same real part, and the imaginary part is going to be multiplied by -1, but multiplying by constants is okay. We need only the independent part. So we have the same, as an independent function, we have the same function for the conjugate of the root lambda. Okay, so in our case, the number A is 1/2 and the number B is 1. So we have the solutions. So let me write these solutions. Okay, let's go back up a little bit. So for lambda 1, for the first root, we have the first solution, e to the power minus t, minus 1 times t. Now for the complex root, we have the solutions, the second one, e to the power 1/2 times t. So e to the power t over 2 times cosine of 1 times t. So cosine t. And the third solution, again, the number is 1/2, so e to the power t over 2. And now I take sine of t. So my general solution y is c1 times, remember the first solution, what was it? E to the minus t. C2 times the second solution, e to the t over 2 times cosine t, plus C3 times the third solution, e to the t over 2 times sine t. So if we have um, a real root and a complex root. For the real root, we write the corresponding function. And for the complex root, we have exponential function combined with multiplied with trigonometric functions, cosine and sine. And we use the real part and the imaginary part of our complex solution in the exponential and the argument of sine and cosine. So for this differential equation, remember in this example, the differential equation was third order. So we need 3 independent solutions. E to the minus t, e to the t over 2 cosine t, e to the t over 2 sine t are the independent solutions. So the general solution is just a linear combination where the constants C1, C2, C2, C3 are real constants. So coming up next, what do we do in case of repeated roots? So this is going to be in the next video. Okay, so until next time.